it's my honor to introduce Dr. Sohong Park. Dr. Sohong Park received his PhD in solar physics in 2010 at NJIT under supervision from Professor Haiming Wang. Since then, he continued to do his research focusing on solar observations and data analysis in Korea, Greece, Ireland, Japan, and now in US at Stanford. In particular, he is interested in estimating and studying magnetic helicity in relation to solar eruptions. Let's welcome him again. And Han, you can start your seminar now.
Okay, thank you, Richu, for your introduction, and thank everyone for having me at this COFFIES monthly seminar to introduce our recent study of magnetic helicity and solar flares. After this talk, I hope we can find some common interesting topics for future research collaboration within the framework of the COFFIES Drive Science Center. So, okay, let me start by addressing the key question we try to answer in this study, which is, does the degree of obeying the sign preference of magnetic helicity in solar hemisphere have any association with flaring activity? If so, why? I'd like to use, the analogy of coffees. Let's say the beans we used in this study, SDO HMI photospheric vector magnetic field data, as well as ghost soft X-ray flare event list. And the main tool considered was magnetic helicity flux across photospheric surfaces of solar active regions. And hopefully the fresh copy that I'm going to serve you today will taste like a little bit of understanding on the deeper solar interior origin of flaring active regions. I'm going to, in 1859, solar flare was accidentally discovered by Richard Carrington without any expectation of such a spectacular event when he was observing and drawing sunspots in his private observatory in Redhill, England. This figure shows his sketch of a flare and sunspots on the day of September 1st, 1859. The first two bright ribbons suddenly appeared in a large sunspot group, which he never saw before. His first impression was that a ray of light had penetrated a hole in the screen, which was attached to the telescope front object glass to attenuate the strong sunlight. But even though he moved the screen, the two ribbons stayed at the same position, and they changed the brightness and shape in time. So he immediately noticed that this is a new discovery. He went downstairs and brought another witness. When they came back, the first two ribbons unfortunately disappeared. Sorry for Richard Carrington. But thankfully, another smaller bright points appeared in a different location. I may say Carrington was quite lucky, but qualified to be the first eyewitness of the solar flare event because he routinely observed sunspots and systematically drew and recorded them, so he could eventually have such a good luck. These are daily sunspot drawings by Carrington. As you can see here, the flaring region rapidly become larger in size, and the number of spots also increased. The spots also show large, complicated, asymmetric, and elongated structures, as well as dynamic motions such as rotation and shear. These are typical properties of large flaring sunspots that we well know these days. Since the solar photospheric magnetic field observation became available in the early 20th century, mainly by the observation of Zeeman splitting, sunspots have been classified with their magnetic structures, called Hale classification. For example, the alpha sunspot is the one that consists of a single spot with one magnetic polarity. Beta is a simple bipolar sunspot group, and gamma indicates many small spots with multiple polarities. Delta spot is the one that two opposite polarity spots are located close to each other so that they have a shared penumbra. As you can see in this figure, in 2000, Semis et al. Examined the relationship between the sunspot group area and the peak X-ray flux for many flaring regions. They found that regions with the larger spot area tended to show the higher value of the flare X-ray peak flux. And regions magnetically classified as delta spots typically have the larger sunspot area as well as the larger flare peak flux. This movie shows magnetic activity of the sun and transient flaring events over the entire year of 2014, which is the peak of the last solar cycle 24. As you can see here, active regions with strong and complex magnetic fields emerge on the solar surface, evolve in time, and sometimes produce large flares. Active regions usually follow the Hale's law. Let's say for solar cycle 24, the magnetic polarity of the leading sunspot is negative in the north, while positive in the south. There is also an active latitudinal belt of sunspots between 0 to 30 degrees in each of the northern and southern hemispheres. In addition, a longitudinal domain of enhanced sunspot activity, known as active longitude of sunspots, was examined. On the right bottom panel, you can see the variation of the Carrington pace for active longitudes over a period of about 8 years. In general, there are two types of Carrington pace increase and decrease, so-called the prograde and retrograde paces, respectively. The prograde pace usually corresponds to the rising pace of the solar cycle, while the retrograde pace seems to be irregular in both hemispheres. In a similar context, we became interested in investigating whether there are any particular heliographic regions of large flaring activity in Carrington coordinates over solar cycle 24. So we decided the Carrington heliographic regions as follows. After then, we collected all active regions observed at every 0 UT over an 8-year interval of 2010 to 2017 and located them into each of the defined heliographic regions. So, for example, the Carrington longitude and latitude of the central position of this target active region are -150 and -18 degrees. So it can be located here. For each of the observed active regions, we calculated the 24-hour flare index. Again, the 24-hour flare index of this active region observed at 0 UT on the year 2010, May 22nd, is 1.7 because it produced B 5.0 and C 1.2 flares on that day. Well, we found a total of about 100 active region samples for the Carrington heliographic region with the longitudinal extent of -180 degree to -135 degree and latitude of -30 degree to -15 degree. Then we calculated the average of 24-hour flare index values for all active region samples in this particular heliographic region and colored the square box with the corresponding flare index value. Repeating the same procedure, we could make this Carrington map of the average of active region 24-hour flare index values. Interestingly, there is a particular heliographic region with remarkably large flaring activity. Now our question is why? And to answer this question, we decided to search for the degree of compliance with the hemispheric sign preference of magnetic helicity in these same heliographic regions. Okay. Now let me briefly explain the hemispheric sign preference of magnetic helicity. Over the past decades, it has been observed in the solar atmosphere that the left-handed helical structures tend to appear more frequently in the northern hemisphere. On the other hand, right-handed helical structures in the southern hemisphere. This is the so-called hemispheric sign preference of magnetic helicity. We should note that this is a tendency, but not a rule. The hemispheric sign preference has been well observed in different kinds of physical quantities, such as magnetic helicity, current helicity, kinetic helicity, and so on. And this sign preference also appears in various features in the magnetized solar plasma. Moreover, the hemispheric sign preference is found to be independent of the solar cycle. This is a summary figure showing the degree of the hemispheric sign preference previously studied for different features in the sun and solar wind. As you can see here, the degree of the sign preference is in the range of about 60 to 80%, depending on the investigated features. This is another summary table. Interestingly, as marked in each of these colored boxes in the table, even for the same feature, but depending on the sample size and observation time and data used, and probably method under consideration, the degree of the sign preference varies quite a lot. And several physical processes have been proposed so far to explain the hemispheric sign preference. This table shows some of the relevant mechanisms in generating or weakening magnetic field twist with respect to the location where the given mechanism occurs, and also which sign of helicity will be produced in each hemisphere. The cases marked in the cases marked in orange represent the mechanism that can enhance the hemispheric sign preference. On the other hand, the mechanism marked in red can produce twist against the sign preference. Meanwhile, we think turbulent flows in the convection zone and various surface flows may reduce or do not contribute to the sign preference. Another mechanism was recently proposed, which is the selection effect on the preferred helicity sign of rising flux tubes in each hemisphere. This selection effect is caused by successful rise of flux tubes in the convection zone that can only overcome the magnetic tension force by the overlying background magnetic field. In these simulations, the initial background magnetic field, Bs, is set up with different values of its strength, and also the rising flux tubes with different signs of helicity. For example, for the top two rows, positive helicity, and for the bottom two rows, negative helicity. The simulation results show that if the flux tube magnetic field and its overlying background field has the same orientation, then flux tubes fail to erupt even for a much weaker background magnetic field, which is about 6% of the strength of the flux tube axial field. And this cartoon illustrates, based on the simulation results, why we can see the same hemispheric sign preference of magnetic helicity independent of the different solar cycles. Even though the orientation of the background toroidal field is reversed as the 11-year solar cycle changes to the new one, the preferred sign of helicity for successful rise of flux tubes will be still the same, which is negative in the north and positive in the south. Okay, from now on, I'd like to present what we have recently worked on. Please remember that magnetic helicity flux can be practically measured in the solar surface, and it can give us some important messages, not only for magnetic field structures formed deep in the solar interior, but also their deformation and evolution through the turbulent convection zone. Okay, here is the data set of HMI active region patches called hubs that we used. The data set consists of about 4,800 co-aligned pairs of hub vector magnetograms at 12-minute separation observed at 0036 UT and 0048 UT, and located within plus minus 60 degrees from the central meridian. We considered only the hubs associated with NOAA-numbered active regions that contain sunspots. Magnetic helicity flux is basically calculated from the surface integral of magnetic helicity flux density G theta here, suggested by Etienne Perriot and Paris group. In this helicity flux density formula, the key is this cross product of relative position vector and the relative field line point velocity for the given two grid points, x and x prime. The field line point velocity u is defined combining the horizontal and vertical velocity components derived from the Dave-Fovian velocity inversion technique developed by Peter Schock with a pair of consecutive vector magnetograms. Here you can see an example of a helicity flux density map for NOAA active region number 11076 in the bottom figure. A localized negative helicity flux is found in the positive magnetic polarity patch on the top right, with horizontal flows showing a counterclockwise rotation. On the other hand, a relatively larger amount of positive helicity flux is typically found in the pair of the main opposite polarity magnetic patches due to a shear motion along the polarity inversion line, as well as rotating flows in clockwise direction. This active region was located in the southern hemisphere, so that the overall helicity flux in this region follows the hemispheric sign preference, which is positive. This is a diagram in which the size of the rectangular boxes indicates the number of active region samples in each of the Carrington heliographic regions that I showed you before for the calculation of the average 24-hour flare index. Now we calculate the percentage or degree of active region samples that obey the hemispheric sign preference in each heliographic region. Here, the colored boxes indicate the degree of the hemispheric sign preference. First, we can find that higher latitude regions in both northern and southern hemispheres show larger degrees of the hemispheric sign preference, which are about 60 to 70%. On the other hand, smaller hemispheric sign preference degrees in the lower latitude regions. In particular, there is one distinct region with an extremely low hemispheric sign preference of about 40%, marked with the arrow. When comparing with the average flare index of the same heliographic regions, we found that this very low hemispheric sign preference region showed the extremely highest flaring activity during solar cycle 24. And this diagram shows the average of the total unsigned magnetic flux for the defined heliographic regions. You can see that there are two regions in the southern hemisphere where the average magnetic flux is relatively larger compared to the others. And those two regions basically show large flaring activity. So for all of the investigated heliographic regions, I made a scatter plots, and these scatter plots suggest that there is a weak tendency of the larger flaring activity in the Carrington regions with the lower degrees of the hemispheric sign preference compliance, as well as with the larger values of the average magnetic flux. Again, the tendency is not very strong, but it's a bit weak. You may wonder why such trend appears, even though it is a bit weak tendency. This recent simulation study again may help us to understand the observed trend. For example, if we assume the background magnetic field is almost the same in the convection zone, then the field strength of a rising flux tube should be larger for its successful rise in the case that the helicity sign of the flux tube is against the hemispheric sign preference. So we think this extremely low hemispheric sign preference region, which produced large flares, has a larger value of the average magnetic flux. And as well known, flaring active regions tend to have large magnetic flux. Moreover, the lower degree of the hemispheric sign preference with the larger flaring activity may suggest that there are localized regions in the convection zone where enhanced downflows and strong turbulence are present. So rising flux tube in that place, that particular place may be deformed by such a strong turbulent downflows, and their magnetic structures become complex to form delta spars and maybe produce large flares. So hopefully more realistic dynamo simulations and helioseismology studies will help us to better understand the formation and evolution of flaring active regions even before their emergence on the solar surface. Finally, I'd like to shortly discuss about some future plans for collaborative research with the COFFIES team members. First, we can extend this study to better understand the origin of large flare in Carrington regions with more active region samples, and also including properties of subsurface flows, especially in collaboration with helioseismology research groups. We can also compare the observational findings with the state-of-art realistic convection and flux emergence simulations. In particular, this is one example, which is under development by colleagues in Japan. Here, R2D2 is a radiative MHD simulation code covering the deep convection zone to the lower chromosphere. Using such simulation code, using this simulation code, a recent study shows that delta spars can be formed by strong downflows in the solar convection zone. And this is another example study in which we may be able to better understand the interaction between flux tubes and turbulent convection flows for various cases. And we can also find out some critical conditions for the formation of complex sunspars. So I guess in terms of the observational findings in this study, and the combination of some recent simulation studies, we think we can probably understand the deeper origin of flaring active regions. So thank you for your time and listening. And please contact me anytime if you have any ideas for future collaborations. I guess I have some chat questions.
Questions? If no one raises hand, we will first address questions in the chat session. Live mentioned a paper that showed flares occur mostly at hill boundaries. Live, do you want to say something?
I'm working on setting it up. Yeah. Let's see. Several years ago, we noticed. No, actually, this goes way back to a student we once had. His name was Phil Dittmer. Way back in 1975, he published a paper pointing out that proton flares seem to occur near sector boundaries. And that sort of died. Nobody paid any attention to it. And then about 10 years ago, Hugh Hudson and I took up this question, and it turned out that flares have a tendency to occur near what we call a Hale boundary on the sun. A Hale boundary on the sun is a neutral line where the polarity is the same as that of sunspots at that position. And it turned out that almost all flares occur within short distance in time, or 24 hours, of such a boundary. And we postulated that that tendency would change when the next solar cycle would come. And indeed it did. We published a paper in AppJ on that, and not much has happened with it since. Now, I'll talk maybe more about it when we have our group meeting later on today. But the conclusion we drew was that maybe active regions were stressed already below the photosphere, so below they emerge. And I was wondering if helicity would show the same tendency. That would be something to look at. Should be relatively easy. So that's what I have to say about that.
Yeah, thank you for the comments. To be honest, I haven't yet checked the hemispheric sign preference in the Hale boundaries, but I think it's worth to check it out. Yeah, so yeah, I think that's a good and interesting comment. So
okay, thank you.
In future, yeah, I will try to also look at the helicity in those Hale boundaries. Yeah.
And we just noticed that with the new solar cycle 25, it's reversed again. So
okay.
So the effect was shown in the transition from 23 to 20, from 22 to 23, and from 23 to 24, and also now from 24 to 25. So it is very solid, and it would be strange if the helicity has nothing to do with that. So, I look forward to see what you can do with this.
Okay, yeah, very, very nice comment. Thank you very much. Yeah. And
there's a few more discussion in the chat. Do anyone wants to speak up? Sushan asked what is a hill boundary, and I think Todd answered that question.
Yeah, and
Any more questions? If you want to speak up, you can just open your audio and ask.
I'm glad to see Bishek Manek here because I didn't expect to see him, but I actually referred to his paper in this talk, and I think that's very nice work to explain the hemispheric sign preference. So, Bishek, do you have any comment or question for my talk today?
Yeah, hi, thanks for the interesting talk. Yeah, I had discussed something similar with Dr. Yang Liu over here too. So what you have done is averaged over the whole solar cycle, right? And plotted as a function of latitude and longitude. What I had discussed with my advisor, Nick Brummel and Yang Liu were sampling out different regions of the solar cycle. So like you have it for 7-year period, 2010 to 2017, I think. So we were sampling out trying to sample out different regions in the time period and trying to measure the exact same thing that you are doing, right? How is there some sort of a flaring preference or helicity preference which depends on time as we progress in the solar cycle. So yeah, what you have done is a very interesting way to think about this work. Yeah.
Okay, yeah, thanks. Yeah.
Thank you.
Okay, if no more questions, let's thank to our speaker today for a wonderful talk and great discussions. Thank you.
Roger, there was
Question. Todd. Sorry, Todd asked, could you say a little more about why the flares are so concentrated in one current region?
So that particular Carrington heliographic region also showed extremely low degree of the hemispheric sign preference. And we checked whether there is any sample bias, I mean, due to a few large active regions, whether actually this lower degree and larger flaring activity happened or not. So we actually resampled, actually we removed some large regions in that particular heliographic region, but here we could see a similar trend. So I don't know actually in the convection zone and deeper interior, maybe I guess there are not. Let's see. The turbulent convective flows, or there may be some strong long-standing downflows in such particular heliographic regions. But yeah, from this study, actually, we cannot answer for that. So.
Well, it gives us an interesting place to look for things that are a little bit different than they are in other locations on the sun. You know, we've looked in the past at different rotation rates too, but the fact that it's at the Carrington rotation rate, you know, may say something about the latitude, I guess. But even so, you know, is there some sort of deeper thing going on? Because you had sort of two regions that were both in the south, and they were separated by what, 180 degrees or something, not quite that much, I guess. So yeah, it's intriguing, I guess, to see if there are other if we could find some other indicators that indicated that the same regions were of some specific or special interest. Because you think that maybe, you know, maybe the supergranular flows are different there, or maybe yeah, I don't know. you can imagine lots of things, right? And if you have a place to look, then that would be interesting.
Yeah, one thing to be careful is, as Todd mentioned, actually the Carrington coordinate I used, actually I didn't actually trace. I didn't actually trace the regions with respect to the latitude, I mean, because the differential rotation, I didn't actually consider that. So to be more accurate, I guess we should actually locate the regions considering the differential rotation at different latitude, so that we can actually better understand the deeper origin.
Yeah, or maybe it's the core rotation, right? You know,
Yeah,
or the
right.
basic convection rotation. I mean, it could be anything. Yeah. And Tail Bay was doing some things about that several years ago, and you know there were certain periods that he found much more common.
Okay. Okay. Thanks. Yeah.
Any more questions? Okay. No. Okay. Again, let's thank the speaker for his wonderful talk and great discussion. Thank you.
Thank you. Thank you.